Okay, this chapter is about vectors. Vectors are used a lot in technology, navigation, physics. We'll see a lot of application questions here in a little bit with the next couple sessions that you'll be able to see where vectors are used. First thing I want to talk about is the definition for vectors. So by definition, a vector is a directed line segment. Okay. Basically, what we'll talk about for the most part throughout the entire chapter is a direction, and we'll use what we know from trig and angles to dictate a direction. We usually go from standard position, and then we'll talk about a length that we call either it kind of goes back to what we were talking about in chapter 8, a modulus, a lot of times is what's referred to, or the magnitude. Okay, so I'll give you kind of a quick rundown here. If I have a point here, let's just say we're at 2, 1. And then, so let's go 3, 4, 5, 6, 7, 8. 1, 2, 3. So 8, 3. I'm gonna let this point here be my what we call our initial point, and this here will be my terminal point. Okay, so your terminal point always has an arrow attached to it, so you can do. The way I had it initially was like a dot here. That's the point, and then the arrow up to it. It's usually the way you'll see it. This, just because of the way we're going to talk about some phrases in a little bit, this is called the tail. The initial point is referred to as the tail, and the terminating point or terminal point we usually call the tip. Okay, so we'll talk about tip and tail. But that is basically a visual of a vector. It's a directed line segment. So I'll give you a couple more here. We'll go to GeoGebra. So you see there, if I can get you can see the initial point here at 1, 1, terminal point here at 6, 4. We got the arrow there, so that's vector. Now, the one thing about vectors is we can move them around. So this vector here, kind of look right here at the moment. It's called 5, 3. And we'll talk about how we get that 5, 3 here in a moment. But as I move this around, that 5, 3 never changes. A and B change. Their position changes. But the 5, 3 vector never changes. So this vector here and that vector there and that vector there, they're all the same vector. Okay, so there's no difference between them, even though their positions are different. Their angle, okay, so the angle, let's see here. When I say angle, I mean direction, but this angle right there, whatever it may be, is the same as when that thing is there and I move the angle there. You see it's the same angle, okay? The length is the same, and that's really what makes a vector or two vectors equivalent, is if the direction and their lengths are the same. Okay, so one of the key things that they ask us to do is to draw a vector. Okay, I just told you how to draw it, and then come up with what we call a position vector. Okay, so First thing we're going to do here is use the initial point 2, 3. So I'll go over to 2 and then up to 3. So this is my initial point 2, 3. And then I want a terminal point at 6, 4. So 6, 4. And all I want to do is that. So that is drawing the vector. Okay. So a lot of times when we talk about vectors, we use like lowercase letters. We use U and V a lot, and they make them bold. Okay. Sometimes you might see the vector symbol above them. Those are the most common. You can use any letter you want to, but we usually use, like I said, U and V. So say, I'm just call this vector U here. If I want to come up with what we call the position vector, basically all we're going to do is figure out what is this right triangle. What is this right triangle that is kind of in the background, or that is creating this vector? Okay, every vector, unless it's horizontal or vertical, is going to be a hypotenuse of a right triangle. So when we ask for a position vector, basically what we're doing is figuring out, well, what is this horizontal distance? Well, that horizontal distance is taking the 6 minus the 2. So I subtract my x's. The vertical distance is taking the 4, subtracting the 3, and that gives me my vertical distance. Okay. Now, something that we do, instead of putting just a notation thing, we put these kind of angle brackets to denote that we're talking about a vector. So when I go 6 minus 2, so 4, and then 4 minus 3 is 1. So the position vector here is 4, 1. So what I'm going to do in GeoGebra to kind of convince you of that real quick is get the point 2, 3, get the point 6, 4. Okay, now if I actually draw in the vector from A to B, you see that it gives the position vector 4, 1, which is exactly what we had. Okay, and this notation is what we use for the most part in the class. The notation that GeoGebra is using here, this is more convenient when you get into a linear algebra course, like after 3 or 4 calculus classes in college. So now what I can do is, if I were to ask this thing, I think I can say vector if I start at 0, 0, and then type in 4, 1, the position vector is essentially what vector would you create here at 0, 0 that would be identical to this one here. If I put those on top of each other, you see that they match perfectly. So those two are the same thing. It just makes things more convenient for us eventually when we're able to take this vector and put it down here to actually basically do a translation of it. And if you think about it, the right triangle that is associated with that vector and the right triangle that is associated with this vector, they are congruent right triangles. Therefore, the hypotenuses are congruent, so the vectors are the same. So that's putting something into or taking a series of points and finding the position vector. Let's talk about some things real quick. I'm just gonna, and I don't have this put in to our into these notes right now, but things that are in mathematics, we have two kind of things that we can describe quantities with. We have what we call scalars, and we have things that are called, or that we use vectors to deal with, okay, to explain. So scalars are things like time, it's on a scale, temperature is on a scale, age, weight, you can come up, there's a lot, okay, but those are things that are scalar, meaning that they can be represented by just a number. So scalars are things that are represented by just a number, okay? Speed is one, okay, and I'll talk about that here in a moment. But vectors, things that have to be represented by a number and a direction, okay, a number and a direction. So I said speed, velocity. Okay, velocity is defined as speed with a direction, or speed in a certain direction. We talk about forces like gravity. Okay, we know the what is it, 9.8 meters per second squared. But that is represented by a vector because it's a force downward. And here's the scalar portion of it. Here's the quantity, and then down would be the direction. Acceleration is a vector. We're going to, like I said, as we go through a lot of this chapter, we'll add to these and talk about these in specific cases. We're probably most familiar with scalars, okay? But vectors are things that they have two pieces of criteria. They have a numerical value that essentially have a scalar, but attached to it then is a direction, okay? Wind would be one, okay? If I say I have a 30-mile-an-hour wind out of the southeast, 30 miles per hour, there's my scalar portion. Out of the southeast, there's my direction. So that being said, when we talk about magnitude, the magnitude is going to be the length of the vector. So magnitude equals length of the vector. Okay. So if a vector, and I'll just call it vector v for now. So if a vector is represented by like a1 comma a2, okay, and remember that is going to be, that's the horizontal distance, and that is the vertical distance. That this vector orientates itself in the coordinate plane. Okay, a lot of times we'll start at 0, 0 and that kind of thing, but sometimes maybe if you're familiar with physics, they call this a horizontal component. They call this the vertical component of a vector. But if, let's say we have a vector, let's say we've got a coordinate plane here, Okay, so I'm going to start at 0, 0, and let's go to there. So they're telling me that this here, that horizontal component is this A1 number. This vertical component here is the A2. So if I want to find the length of the vector, so this is V, so the way we say the length is that we're going to put these absolute value bars there. We're going to say that, let's write it here. The magnitude, so this is the way we read, the magnitude of vector V is equal to, if you think about this is a right triangle, we're just going to figure out this with the Pythagorean theorem. We would say A sub 1 squared plus A sub 2 squared. That would equal this vector squared. So then we take square root of both sides to isolate the length of the vector. Okay. And remember that when we're finding the length of something, it's always got to be a positive number. So that's our magnitude. Okay. Okay, now if I wanted to find the direction of the vector, so the direction is going to be that angle right there. So here we would say, I'm going to know that number and that number. So I'm going to say that theta is equal to tangent inverse of A sub 2 over A sub 1. And that should give me my theta, that should give me my direction. Okay. Now if we're working, and you might see this from time to time, this is if I'm able to, if I know the position vector. Okay, we should be able to find, per the last example, just do the subtraction. But let's say that you don't want to go that route. Let's say that we've got this vector here. This is x1, y1, and this is x2, y2. You can say that the magnitude of vector v would be x2 minus x1 squared plus y2 minus y1 squared. You've done this before. So that's just the, again, Pythagorean theorem. This is actually the distance formula. And then theta here in this case, so theta would be still that angle there. You have to insert a horizontal here. But theta now would be the tangent inverse of that distance there, which would be the y2 minus y1, over this distance here, which would be the x2 minus x1. So you might see varying situations where this might be appropriate or this might be appropriate. In order for two vectors to be congruent vectors or equivalent vectors, they have to have the same direction and they have to have the same magnitude. So that's what we're going to try to do here with this example, is just demonstrate that they both here are indeed equal vectors. So first thing I'm going to do, let's just look at vector u here and let's find its magnitude. Okay, so its magnitude, so it's going to be the 4 minus the negative 1, so it'd be 5, and we'll square that, so we get 25. And then we're going to add to it, so we get the 6 minus the 2, which is 4, square that, I get 16. So that's going to give me root 41 as the magnitude of u. Okay, now theta is the tangent inverse. Okay, now it's that y distance that I just found. So that y distance was 4 divided by the x distance, which was 5. Okay, and we'll talk a minute. I'm going to go grab the calculator here in a minute and evaluate that if I need to, depending on what this next one shows out to be. So now I'm going to look at vector v. So v, So now I'll take the 5 minus the 0, square that, gives me 25. Take the 4 minus the 0, square that, gives me 16. So I get root 41. Okay, that's not enough to say that the vectors are equal vectors. They're the same length, but we can have a lot of vectors of the same length that are not the same thing. I'll show you that here in a moment. But now if I go theta, I would go tangent inverse. Okay, so it's this y distance, which we figured out was 4, divided by that x distance, which was 5. And now you see there and there, the thetas are the same. So that tells us that u is equal to v because they're both the same length and the same direction. If I had something like this, let's say I've got a vector, let's go from 1, 1 to, let's go 1, 2, 3, 4, and then up 2. So I got that vector 4, 2. Now I could also have a vector that does this. Starts there, 1, 2, 3, 4. Let's go this. Let's go 2, and then 1, 2, 3, 4. Okay. If I give you the distance of these two things, and let's actually move this one away so that's not intersecting. If I ask for the distance of that vector from A to B, and this one C to D, they're both the same length, which you can see obviously that they're not both going in the same direction. Okay, the angle for this one, the theta for this one here, would be if I extend that, okay, and then find the angle right there. Okay, the direction of this one would be extending here, okay, and then finding that angle. And that angle there is much bigger than this angle here. So you can have vectors that have the same length, but different directions. Therefore, they're not the same vector. For the same reason or same logic, I guess, you could have two vectors. Let's say I've got a vector here. I'll make it red, make it a little bit bigger. That vector. And then let's say we've got, so let's go out to 8, 4. That vector there, let's make that blue. We've got the blue vector, and we've got the red vector. They're obviously both going in the same direction, on the same trajectory, but they're not the same length. So they have the same direction, but different lengths. They're not the same vector. So that's nice. So this next stuff kind of gets into talking about vector addition, and really what I'm going to do here is just demonstrate, just for the sake of shortening this session a little bit, I'm just going to get into just a visual of what we refer to as vector addition. Okay, and this is on my website under section 9.1. If you guys want to download this yourself and mess around with it, but it says the vectors below can be changed by grabbing the arrows and moving them. Okay, so move W, grab this one, V, and U. I've got them all stuck here at 0, 0, so they're kind of position vectors, but I can move them around if I want to. So that W and that W would be the same. Okay, so you can do those things. So it's trying to make sure that your arrows terminate at grid lines. So if you're gonna mess around with this, and I've got it set up right now to where they snap to a grid, so they snap to that like intersection there. when you're messing around with this, don't kind of do that because it's going to be very hard for you to get the visual that is demonstrated here with this applet. So this applet only works for showing the sum of two vectors. I haven't spent a whole lot of time to demonstrate three vectors added together. But nonetheless, this should be something we can do. So let's just say I've got these two vectors here. Don't even worry about W. I've got U and V here. What we're going to be asked of here pretty soon, probably in the video on Friday, we'll talk about this, is can we algebraically add these two vectors together? Okay. What I want to do visually is basically right now these two vectors are positioned, so they're sharing initial points. So they are what we call tail to tail right now. But we can only add or subtract vectors when they're tip to tail. Okay, so it doesn't matter which one I do this with, but I'm going to move one of these so that the tip of the other one is touching the tail of, in this case, the pink one. So I do that, and when I do that, so tip to tail, that's the tip of this one to the tail of that one, what happens is that we get this red vector to show up. If we go from the initial starting point of the gold and follow the pink one, we would get to that position right there where my cursor is, and this red vector shows up, and this red vector actually shows us a little bit more of a more efficient manner of going from 0, 0 to that point right there. Okay, and so this would be the sum of that vector and that vector. Okay, so a lot of times, so I'm gonna do this. I'm gonna say, I don't know if I can do U plus V. Okay, so I can do the vector addition here. I've got U identified and V identified. So all I did is I typed in U plus V down there in the input, and it put that vector in. Okay. What I want you guys to think about here, and this is kind of what I said at the beginning. If you understand this concept here that I'm about to explain to you, vectors throughout the whole chapter should be pretty easy. Let's imagine that we took, like, let's say this is so the grid is our classroom, and we're looking at our classroom from the ceiling. We're all sitting on the ceiling, looking down on the floor. So we got a bird's eye view. Okay, and so let's say the tiles here. So these grid lines are the tiles on the floor. Let's say we place a person in a rolly chair right there. Okay, and it doesn't matter that we put them at 0, 0. They could have been put anywhere throughout the coordinate plane. We'll traditionally do some algebra that gets us back to 0, 0 to make things easier, but it doesn't matter. So we got a person right here in a rolly chair. Okay, and what I'm going to ask is I want to have person number 1 standing right here, and I want them to push this person in that direction. I want them to push in the direction of V, and let's say that, I don't know the length of this. Let's see if we can get a length on here. So the length, I thought that'd be a problem. V. We could take 25 plus 36. Take the square root of that. Can I just do this? I can't. So maybe I can do this distance. Okay, so yeah. so that length right there is 7.81. Just for convenience sake, let's just do distance of u as well. So u is terminating at 5, -3. So we'll go from 0, 0 to 5, -3. So that's distance u. And now I'll just do that f as well. So distance of 0, 0 to 10, 3. Okay. And that's going to give me 10.44. Okay. So this was V. This was U. So let's just color these real quick so we can keep them straight. So this one will be okay. So if I get back to that scenario I was giving, so we have a person in a rolly chair here, and they are going to get pushed by person number 1, and I'm going to ask them to push in a certain direction. So I give them a theta, and I tell them to push with 7.81 newtons. Okay, maybe from physics you have an understanding of newtons here, unit of force. And then at the same time, I have person 2 standing here, and I ask them to push in that direction with 5.831 newtons of force. And I ask them to do that simultaneously. Okay? So somebody's pushing in that direction, somebody's pushing in that direction. And they do it simultaneously. Okay? And what's going to happen if they do that, the person in the rolly chair isn't going to take the gold path. They're not going to take the purple path. They're going to take a combination of the two. They're going to take this path. Okay? They're not going to have, a complete, we're going to add those two numbers together and get the length of this one or the amount of force that would be required to get to that point. But that 10.44, that number there, will always be less than the sum of those two things. That's kind of the idea of vectors and forces. You can do the same thing. Let's say if you were, if you were standing right here and you had a rope tied to this person in their wheelie chair, and then you had another person here with a rope tied to them, and we were able to pull with a certain force that we were able to control within these directions. And I told you to simultaneously pull on this person in the wheelie chair with those forces. That person is going to be slingshotted that direction. Another way of visualizing it is exactly what we did with moving these tip to tail, is if I were to tell you, instead of doing it simultaneously, let's go back to this situation here. These are my two vectors. Let's push this person along this vector here with that 7 point whatever it was magnitude. And once they come to a rest, let's have person 2 push that person with that 5.8 magnitude in this direction, and they'll come to a rest. And then my question will be, okay, go back to the starting point. Go back to 0, 0 right here. How can I go from 0, 0 to get to the same ending point of 10, 3 without having to go through these two individual movements? Well, I would go across this vector here, u plus v. Okay. And now what will happen is that we know from geometry that the shortest distance from 2 points, or between 2 points, is a straight line. So if I want to go from 0, 0 to this position right there, efficiently, it means the best way to do it is go along the red vector. Inefficiently, I'd go along the gold vector followed by the purple vector. Okay, so this is sometimes called the triangle property of vectors in vector addition, but a lot of times it's also called the parallelogram property because we can do this. So I'm just going to cut and paste here and get another vector of u. I think I got a couple here, but it doesn't matter. But if I do this and then cut and paste this one, okay. If you, I just want to hide this u plus v for a moment. Maybe I can't. Let's do that. If you construct the parallelogram of these two vectors that were position vectors starting at 0, 0, they were both tail to tail there, then the sum is always going to be the diagonal that starts at the two tails and comes together then or finishes at the two tips. So that's maybe another way that you can visualize how to do the summation of those things. But we can do, if I want to do, let's put that one there. I don't want to show that right away. Let's go back to this W. So now let's say I want to then add W to these. I don't want to show that one. But let's say I did that. So follow vector V, then follow vector U, and then follow vector W. The final vector would be, when we call it the resultant, that vector would be from 0, 0 to there. That vector right there would be the combined effect of all three of these vectors. So if we were to put them all, let's get rid of that red one real quick. Put them all right there and say, okay, let's put this person in a wheelie chair. And let's put three forces on that person simultaneously at the same time with three different magnitudes. Where's that person going to go? Well, that person is going to go, so I'll go Control C, V, Control C, V. So put those together, okay? So it would take me from G or 0, 0 along that red vector. If I put this vector, that vector, and that vector, their combined effect on somebody in a wheelchair would get them to right there. Okay. Now, what's kind of interesting here is, let's see here real quick. Try to figure out what this A vector, where it's at, what's being called, 9, 7. Okay. So let's get rid of this one here real quick. And let's say that instead of going gold, purple, then blue, we went gold, blue, and then purple. Does it still give me the vector right there that is 9, 9, 7? What I had earlier, I think. Let me just go back, double check. Yeah, so 9, 7 here when we went gold, then add to it purple, then add to it blue. Or if we go gold, then blue, then add to it purple, still gives me the same vector, 9, 7. And basically what that tells us then is it doesn't matter the order that I add my vectors. So vector addition is commutative. One last thing, if we do vector subtraction, which we do eventually, all we have to do is say, let's say I've got vector v here. if I wanted to show the opposite of v, so negative v would look like that red vector there. And I think what you're seeing here is that they'd be the same length. That vector and that vector are the same length, but they are opposite one another. There's a 180-degree rotation here. So these are opposite rays. And that's how we identify vectors. So this would be, like I said, vector v. And let's see here. Where'd that? There it is. And this one here would be the opposite of v. So that'd be opposite of v, and this would be v. If I want an opposite of u, so opposite of u is going to go this direction. I'll give you a look at that. Opposite of u. If I want to go opposite of w. And GeoGebra always puts things back, puts your vectors when you're doing this work, always puts them at 0, 0, because that's the convenient thing to do. Like I said, right now, so this will be Wednesday. I'm not putting an assignment up yet. I want you to work on that chapter 8. I want you to take notes over this. We'll pick up with some more of this stuff on Friday, and I'll post an assignment on Friday for you.